With the recent advances in AI, many people are saying that within a few years, computers will reach the level of the so-called artificial general intelligence.
We have no idea how AI actually works, and so it's getting a lot more powerful.
The AI edited the script so that the shutdown command would no longer work.
But is it really feasible? Of course, if this were to happen, it would have profound implications for all of us. But the question I would like to ask is, can a computer truly reach the full capacity of the human mind?
It's smarter than us, right? There's no way we're going to prevent it getting rid of us if it wants to.
Some say we're a threat that will take over, and that humanity will end.
Of course, computers are very efficient at many tasks, much more efficient than humans. For example, computers are very good at crunching numbers, meaning adding, multiplying numbers, and so on. Even calculators could do that much better than humans. So it would be natural to assume that computers are good at math, right? Or are they? In today's episode, I will show you that actually computers are not good at math. They are not nearly as good as human beings. And when I say math, I mean the real mathematics. And real mathematics is not about crunching numbers. It's about general statements about numbers that apply to all numbers at once. And in this territory, as we will see, computers are lost. They hit a wall, a hard wall, that I would like to call the Turing Wall, in honor of Alan Turing, the father of modern computing, who was one of the first humans to recognize the existence of this wall. We'll talk about all this and much more in this episode. Join me in the aftermath. We are exploring together the question whether a computer can reach the full capacity of a human mind. Now, I'm a mathematician, so I would like to be more focused and talk about mathematics specifically, and I'd like to share my knowledge with all of you. And let's narrow it down even further to the part of mathematics that deals with natural numbers. When I say natural numbers, I mean numbers like 0, 1, 2, 3, 4, 5, 6, and so on. So let us ask the question, can a computer be as good as a human in dealing with questions in mathematics related to natural numbers? The answer might surprise you because of a very important distinction that is not usually made between different types of statements about numbers. Statements about specific numbers, what I earlier called crunching numbers, and general statements about numbers. And it is in the domain of the general statements about numbers that the computers hit a wall, the Turing Wall. Computers cannot reach the capacity of a human mathematician in dealing with natural numbers, numbers like 0, 1, 2, 3, 4, 5, and so on. This follows from some fundamental results by Alan Turing, whom I already mentioned, the father of modern computing, Kurt Gödel, the author of the famous Incompleteness theorems. And the third is Alfred Tarski, and I'm very happy to introduce him to you because he is the lesser known of the three, even though he deserves a lot more credit for what he has done in this domain. Alfred Tarski was a professor at my university, University of California at Berkeley, which is basically just a stone's throw away from where we are right now. He was a professor here for more than 40 years. And he was a founder of our program in logic and methodology of science. His undefinability theorem that I'm going to explain to you, not necessarily in this episode, but in the next episode or in the next few episodes, is extremely important for understanding the questions that we're discussing. The first thing to understand is that there are two different types of statements one can make about natural numbers. Type 1 is a statement about specific numbers, such as 3 plus 5 equals 8, or 12 plus 13 equals, what does it equal? 25. Or 7 times 5 is 35. And of course, computers are very good at dealing with these types of statements about specific numbers, which I earlier called number crunching. You don't even need a powerful computer to deal with that. A calculator will suffice. And now, type 2 statements are general statements about numbers, which are applicable to all natural numbers, 0, 1, 2, 3, 4, 5, and so on, at once, not about specific numbers, all numbers. Here's an example. Every number is either even or odd. That's a type 2 statement. And mathematics is really about type 2 statements, general statements about numbers, not statements about specific numbers which calculators can handle. Here is another statement of this kind, the famous Fermat's last theorem, which took 350 years to prove. It says that there are no natural numbers x, y, z all greater than 0 and another natural number n greater than 2 such that x to the n plus y to the n equals z to the n. Again, this is a statement of type 2, a statement about all natural numbers at once, not a statement about specific numbers. So, looks like we have a problem here, right? How can we possibly encode a statement like this on a computer? The point is that we can't transcribe a type 2 statement as a collection of type 1 statements. If we were to do it, in the case of every number is either even or odd, we would get the following collection of statements about specific numbers. 0 is even, 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, and so on. And we can continue like this for a long time. But the point is that computer's memory is limited. It's finite. It cannot possibly store all of these statements for all natural numbers. That's why type 2 statements cannot be reduced to type 1 statements. So what to do? So mathematicians and computer scientists got together and they found a clever way to circumvent this problem, that you can't just represent a statement of type 2 as a collection of statements about specific numbers of type 1. For that, we use what's called formal systems. Formal systems is a kind of a formal language, very much like a programming language, if you know what I mean, where you have certain symbols which can stand for natural numbers or operations on natural numbers such as addition, multiplication, and so on. And this formal system is capable of expressing statements like every number is either even or odd. So what does it mean to say that number x is even? Think about it. It simply means that x is equal to 2 times y, where y is another natural number. Say x is 6, it's equal to 2 times 3. So if we say y equals 3 and x equals 6, we get indeed that the equation x equals 2y is satisfied. Likewise, to say that a number is odd simply means that x is equal to 2y plus 1. Number 7 is equal to 2 times 3 plus 1. And so this is what the statement that I talked about earlier, every natural number is either even or odd. This is what it looks like in this formal system, in this formal language that we can use to program our computer. Now, it may look a little bit complicated, but bear with me, I will explain all the symbols in it in the next episode. The point I'm trying to make is that using this concept of formal systems, you can indeed encode statements of type 2 without breaking through, the finite memory of a computer. Then what? We have to find a way to distinguish between statements which are true and which are not true, right? So the statement encoded this way, that every number is even or odd, is true. But a statement that every number is even is not true. So how can a computer know which statement is true and which one is not? So a formal system actually comes with a kind of initial seed, with a bunch of statements written in the formal language of that formal system, using the symbols that are part of the alphabet, of the vocabulary of this formal system. We have to stipulate, we have to select in advance some statements that we say are true, are valid. These are called axioms. That's very important. That's the initial seed of the formal system, the axioms. For example, one of the axioms in a formal system that services natural numbers is x times y plus 1 is equal to x times y plus x. That's one of the axioms of a formal system that services natural numbers. Okay, so far so good. We have found a way to encode statements of type 2 by using this symbolic language and the so-called formal system so that we could program them into our computer. We have selected certain statements that we take for granted, which we call axioms. And after that, we actually have to introduce some rules which enable us to produce new statements from the ones we have already established before. So there are certain rules which are called rules of inference. One of them is the famous modus ponens, which says that if we have already established A, and we have already established A implies B, that means we have just established B. That's one of the ways that we can produce new statements that we consider as established, as valid statements in our formal system from the initial seed, which is the bunch of axioms that we started with. So using a formal system, we can now run our computer that we have programmed with this formal system, with the axioms and the rules of inference and so on, and it will produce or print out all the statements that are valid in this formal system, starting with axioms, but then also things that you can get from the axioms by following the rules of inference. Those are called theorems, by the way. So a computer will indeed run and keep printing out or keep producing on the screen more and more statements of this nature. I'd like to call them provable statements, theorems. Theorems are statements which can be obtained or derived from the axioms by using these rules of inference. Okay, so looks like we have solved the problem. But unfortunately, far from it. Far from it. Because it turns out that this way we cannot get all true statements. We simply cannot. It's not a matter of opinion. It's a hard fact. We will produce a lot of true statements this way, those provable statements, those theorems. But we will not be able to produce all true statements about natural numbers. How interesting, huh? So let me summarize. A computer cannot produce this way all true statements. That is a statement of the famous Tarski Undefinability theorem, which is actually closely related to Gödel's incompleteness theorem, and people often invoke Gödel's incompleteness theorems in talking about limitations of computers. But in my opinion, actually, it is Tarski's undefinability theorem that sheds more light onto the whole subject. The basic thing to understand here is that according to Tarski undefinability theorem, formal systems cannot in principle produce all true statements. Computers work with syntax, with symbols. Computers use axioms and rules of inference in a formal system. And this way, they produce a lot of true statements, but not all. Put differently, formal systems and computers simply cannot handle the truth. Let me say it again, in the words of a famous actor. Formal systems
can't handle the truth.
What I have just described places a fundamental limit on what computers can do in principle in regards to general statements, the type 2 statements about natural numbers. They hit a wall, the Turing Wall. In fact, Alan Turing, the father of modern computing, wrote, "The class of problems capable of solutions by the machine can be defined fairly specifically. They are those problems that can be solved by human clerical labor, working to fix rules and without understanding. Without understanding." Now, there is a lot to unpack here. I have to tell you in more details what formal systems are, what rules of inference are, what axioms are, what theorems are, what provable statements are, what true statements are. And we will do that in the future episodes. But there is one important thing that I want to talk about before we close. And that is the fact that actually truth cannot be defined within a formal system itself. That is a point which is often lost these days. Formal systems are not designed for the notion of truth. That is another take on Tarski's undefinability theorem. To have the notion of truth, you have to introduce some additional data. You have to introduce some additional information. Mathematicians call it a model. Not the kind of model you may be thinking about. A mathematical model is something that you need to have a notion of truth regarding various statements in a given formal system. A good analogy here would be formal system and a model is like map and territory. Formal system is like a map, and the model is like a territory. Or if you will, it's like, a description of a tree or a picture of a tree and the actual tree. To have the notion of truth, a formal system is not enough. You need to augment it with a model. And there are many different models. That is a point which I will address in the next episode. I talked about formal systems as a way to represent general statements about numbers, statements of type 2, and to encode them in a computer and to circumvent the problem that computers have finite memory. So you may be wondering whether this is the only way to do it. And indeed, in recent years, a new approach emerged, and that's the approach of the large language models, the LLMs, such as ChatGPT, Gemini, and so on. So you may be wondering whether through that approach we could achieve, we can reach all true statements. something that formal systems can't do. Unfortunately, in my opinion, LLMs are even weaker than formal systems. And the problem is that the way LLMs work is that they work with the corpus of all human knowledge that has been accumulated up to now, and then basically it's correlating all this data and aggregating all this data, clustering all this data, and trying to find statements that are likely to be true, given all that. But you see, mathematics is not about statements that are likely to be true. When I say every number is either even or odd, this is something that has been true forever and will always be true. We don't expect that next year, all of a sudden, it is not true. You see, in mathematics, the notion of truth is clear-cut. And I will explain in more detail what it is. This will involve this notion of a model and so on. But one thing for sure is clear, is that we cannot rely on the technology which simply uses what's more likely to address true statements in mathematics. I'll give you a simple example. 2 plus 2 equals 4. Now, a ChatGPT, in pondering whether it's a true statement or not, may take into account a joke someone made. A comedian could have made a joke somewhere saying 2 plus 2 equals 5 that got a lot of likes. So for all we know, that statement, for some reason, could have an inordinately large weight and would be taken into consideration by the computer in analyzing whether 2 plus 2 is equal to 4. But every human being knows that 2 plus 2 is equal to 4. You don't need to know what has ever been said about that. Of course, LLMs are extremely powerful and extremely useful. It's an amazing tool that I'm using all the time and all my friends. I love it. But when it comes to mathematics, formal systems really represent the only game in town in terms of how computers, in principle, could handle general statements about natural numbers, statements of type 2. And that's a very important point to understand. And, once again, as I mentioned, within the framework of formal systems, yes, computers can produce a lot of true statements. These are the provable statements of the formal system. But according to Tarski's Undefinability theorem, these are by far not all true statements. This is what I meant when I said that when it comes to general statements about numbers, computers hit a wall. Computers hit a wall, the Turing Wall. That's all the time we have in this episode. But before I go, I want to talk about a question that I posed in episode 2. Remember, in episode 2, I talked about three-dimensional sphere, and I invited all of you to share your ideas about how one could, in principle, imagine a three-dimensional sphere. Now, I don't want to repeat what three-dimensional sphere is. I talked about it in detail in episode 2, and again, you'll find a link to episode 2 in the description of this video, if you're interested. What I would like to do is to nominate a particular answer from one of the comments on the episode 2 on YouTube as one of the best, in my opinion, one of the best answers. And so this answer comes from the handle Autumn in Toronto. That's a lovely handle. And here's what it says. Let's imagine insects living on a plane. The insects have no vision, but run all over the surface of the plane, that is. And so suppose a sphere lies on this plane, so it touches the plane at a single point, which the insects will not perceive as an obstacle. It's just a single point. But now let's assume the sphere begins to sink through the ground, sink through this plane. At the intersection with the plane, a circle is formed. That is to say, a fence. That's a good way to describe it. Moreover, as it sinks, the fence first increases in size. The circle first increases in size until it reaches the largest possible side. That's going to be at the level of the equator, when the equator passes through the plane. And then it starts shrinking until, again, it shrinks so much that it becomes a point. And so likewise, says Autumn in Toronto, a four-dimensional sphere could be placed on top of our three-dimensional world. At first, we don't notice it. But as it starts to sink, the intersection with our world, our 3D world, will start looking like a small sphere, which becomes bigger and bigger. It reaches a maximal size, and then starts to shrink and finally disappears completely. I love this description, and actually I'm going to demonstrate something for you. May I have the balloons? Here, right here. I'm going to demonstrate it for you, this beautiful idea of how to represent a 3D sphere. And I'm going to use a balloon. So here I got a bunch of balloons, okay, different colors. Which color should I choose? What do you think?
Orange.
Orange. Okay, orange it is. So I'm going to use the fact that even though our physical world, space-wise, is three-dimensional, the space we live in is three-dimensional, if you add time, you get four-dimensional space-time. So in a four-dimensional space-time, a balloon, well, imagine the balloon is actually contracted to a point. So our starting position would be a point. I can't demonstrate it properly, but you can imagine it. And then I start blowing it up. So, you see, the sphere becomes bigger and bigger until it reaches the biggest possible size, and then it starts shrinking until, again, it collapses into a point. And imagine that it collapses into a point. That, ladies and gentlemen, is a four-dimensional space-time representation of a three-dimensional sphere.
Did you get it?
Yeah. I did, I felt it. It's hard to describe.
So I encourage you, as before, to please leave your comments, leave your questions. And I promise you, I may not reply to all of them, but I read all of your questions. That's not the only way to think of a three-dimensional sphere. And in the future episodes, we'll talk about other ways. In fact, I'm going to enlist the help of a dear friend of mine, Eric Weinstein, who is a world expert on all matters related to three-dimensional spheres and much more. So stay tuned. I'm going to leave you with the wise words of a great mathematician, Michael Atiyah, one of the greatest mathematicians of 20th century and perhaps of all time. In the broad light of day, mathematicians check their equations and their proofs, leaving no stone unturned in their search for rigor. But at night, under the full moon, they dream, float among stars, and wonder at the miracle of the heavens. They are inspired. Without dreams, there is no art, no mathematics, no life. So let's not forget to dream. That's all the time we have. Thank you for watching, and see you on the next episode of the Aftermath.